maybe you can start recording.
Right. Well, good afternoon, everybody. Thank you for joining us. I'll leave it to Gosia to do all the introductions, and then we'll kick off.
Yep. So, yes, hello everyone, and welcome to today's presentation. My name is Gosia Szepulska, and I'm the Southeast Branch Chair. And I would like to welcome you all to the Southeast Branch webinar. Today's presentation is Pipeline Designer's Guide to Cathodic Protection, which is being presented by Ken Lax from Coronal Consult. Before we start, I would like to ask everyone to mute their microphones and turn off the camera, since this helps with the quality of this call. And there is a chat facility available, so you can type your questions or post your comments, and we'll be answering those questions in the end of the presentation. If we can answer your questions on this call, we will respond online. So the last thing, the session is being recorded and it will be available on the Pipeline Industrials Guild's YouTube channel. So thank you, Ken, for agreeing to do the presentation for us, and over to you.
Thank you, Gosia. Well, as we're not, let me just get this right. As Gosia said, this is designed for pipeline designers, and specifically for pipeline designers who are not corrosion specialists. The aim isn't to turn everybody into being specialists, but just to make the pipeline designers aware of some of the things that can be done to help cathodic protection. My colleague and I, Richard Lindley, and I have prepared this for you. We've both got a great deal of experience in these sort of things. We're not aiming to cover every variation that can possibly occur, but we're certainly hoping that you'll get some benefit from it and that you'll feel it's not been a waste of your lunchtime. This is actually the 5th presentation we've made on behalf of the Southeast branch of the Guild. The previous topics started with the basics on cathodic protection, absolutely basics. And that presentation has been particularly well viewed. I think we were just discussing earlier, there's been over 4,000 views of that, which is nothing compared with Barbie dolls and other things, but in the particular one area of specific engineering in the pipeline world, it's quite interesting to see how many people were interested to learn more. And we covered things that perhaps aren't so obvious: solar farm effects, stray currents, high-speed trains. And these are all available on the Guild's YouTube channel. So what we hope you'll get out of today is an understanding of the issues surrounding external corrosion protection. Although it's called a cathodic protection presentation, we do actually discuss quite a lot about coatings, because they're an integral part of the external corrosion protection system, and they do have a major impact on the effectiveness of cathodic protection and on the design. And as Gosia said, please raise questions anytime. Somebody will be marshalling those questions, and at the end of the presentation, we have allowed a period of time to discuss those. Now, mainly this presentation is based on electrically continuous carbon steel pipes. There are some features that relate specifically to these pipes that don't relate to cast iron and ductile pipes. And obviously there are a lot of members of the Guild who are concerned with water. And it's the water industry traditionally that uses the cast iron and ductile iron pipes mostly. And there are some important differences to take account between ductile iron and cast iron pipes. But nevertheless, you I think if we stick to assuming the continuous carbon steel pipes, there's still a lot of lessons to be learned for people who are only interested in cast iron and ductile iron. So we're going to have a quick run through the basic cathodic protection electrical circuit, because it's important that you understand this. And I've got no shame in repeating it. We've said it in every presentation we've made, because unless you can grasp these very simple principles, you really won't have much luck in understanding the rest of the presentation. But cathodic protection is, although it's an electrochemical process, and we could spend a lot of time going through the electrochemistry and the kinetics of it all, but really it all boils down to being a simple electrical circuit, rather like a flashlight. When you're looking at a flashlight, and there's a resistance created by the bulb in the flashlight and the cables connecting it. And the brightness of the lamp, the bulb, depends on how much current goes through it. And that's dependent upon how much voltage you've got to begin with and how much resistance there is in there to oppose it. So that's the basic electrical circuit. You have your power source and you have a load, and nothing happens until you switch it on. And when you switch it on, there's a current path from the source through the load back to the negative connection. And that basically, you can replace the load or the power source with the anode here and the load with the pipe. And normally the anode is buried in the soil to a test post above ground. There is a cable, and from the test post above ground, there is another cable down to the pipe. So until that link there is made, there's no current flow. When you make the link here, the current can flow from the anode through the link, through the cable to the pipe, and back through the soil to the anode. So it stands to reason that if you don't connect your anode to the pipe, you won't get any cathodic protection. If there are obstructions in either one of these parts that reduce the current, then your cathodic protection won't be very good. So you might say that if you put something that covers that defect, like a big rock or a piece of plastic or something non-conductive, then the current won't be able to flow through there. If you have a big rock close to the pipe, then the current won't reach the pipe, it will go around it. Rather analogous to if somebody is hiding behind a tree and you direct a jet of water at the tree, they will be dry because the water will hit the tree and then it will go around the tree on either side and then meet up at the back of the tree. So stones in the ditch and obstructions like that can affect your cathodic protection effectiveness. Now, there's a myth that I find is prevalent amongst pipeline designers, is that if the coating is defective, then the cathodic protection is there to provide the protection. And that's what it is. The first line of defense against external corrosion is the coating. Where that's damaged, then the cathodic protection current will be able to reach it and it will stop the corrosion. Unfortunately, that's not always true, because when we design a cathodic protection system, we get guidance from the standards and textbooks that tell us how much current we need to think of providing. And for example, in this country, there are a lot of pipes coated with fusion bonded epoxy coatings. And the standards recommend something between 0.4 thousandths of an amp per square meter to 0.7 milliamps per square meter. But in the standard, we do say these values are based on the assumption that the pipeline has been built correctly in accordance with the standards. So if you suddenly come across a pipe which has been handled very badly and the coating's been damaged and it's been thrown in the trench and there's obstructions in the way to stop the current getting there, these figures won't work because the designer will not have allowed enough power or current for the cathodic protection to deliver that much. It's a bit like having too small a motor to drive a very, very big vehicle. It just won't work. So it's wrong to think that all of the mistakes made during construction that damage the coating or obstruct the current to flow to the pipe can't be taken care of by cathodic protection. It's not a universal panacea. It's not a fix-all for coating damages. There are a lot of standards that relate to cathodic protection, but the principal ones I've listed here so that people might be able to refer to them and read them if they wish. The titles, by the way, are not the full titles. It's just my summary of what the standard actually covers. So we've got ISO 15589-1, which deals with cathodic protection of online pipelines, and -2 is offshore pipelines. Then we've got 50443, which is the effects of electromagnetic interference on pipelines, which we're going to discuss a little bit later, which is something that pipeline designers need to take into account when they're thinking about the routing, coating selection, and monitoring facilities. 18086 relates to AC corrosion protection criteria, which are a bit more complicated than cathodic protection criteria and have to be taken into account. 14505 is one that's perhaps not well known to pipeline designers. It's the standard for the protection of complex structures. And in this context, a complex structure isn't a complicated structure per se. It's a structure which is earthed. And you can imagine from the little sketch we did of the electrical circuit for cathodic protection, that if you've got something that's connected to a very, very low resistance, then it's going to take all of the current, because electrical current's a fickle thing. We often say you can compare it to the flow of water, which is, like all analogies, doesn't hold up for every case. In reality, cathodic protection current and any electric current will take every possible path available to it. It's just that the very high resistance parts, the amount of current that arrives is negligible. So if you connect two things together, like a pipeline and a very low resistance earth, the majority of the current is going to go to the earth and not to your structure. So there are special techniques we can use, which are described in these complex structure standard. And I'll talk about that in a little bit more detail later on, because it's an important thing for pipeline designers to know about. The 16440 is also a very useful standard. It deals with the design, construction, and maintenance of steel case pipelines. And cathodic protection people don't like steel case pipelines very much, because once the carrier pipe is inside that pipeline, we're very much restricted on what we can do to stop any corrosion. And you might think, well, there won't be any corrosion because it's in this pipe and it's just full of air. The reality is that the casing is seldom properly sealed. So you do get air and water in there. And once that water's in contact with the internal pipe, or once the air inside is moist, then there's the risk of corrosion if there's any coating damage. And the risk of coating damage is greater for a pipe inside a casing because of the damage that often occurs when they're pulling it through. I'll talk a little bit later about the spacers that we put on the pipes to keep them electrically isolated from the casing, and to keep them centralized in the casing. But they're very often poorly installed. And instead of being evenly spaced and separating the pipe, you end up with a whole collection of them at one end where they've pulled the pipe through. So steel case pipelines, we we like to say in the corrosion protection standards that unless they're absolutely essential for continued mechanical strength and safety reasons, they should be avoided. And 21857 is a relatively recent standard that was published in 2021. It's the first pipeline standard that deals with the issues of electrical interference. And that also needs to be considered by pipeline designers. There's a lot of useful tips in there because electrical interference doesn't just come from AC power and DC power. It also comes from tidal variations, extraterrestrial space weather events, such as the recent, you may not have picked it up, but there was quite a large electromagnetic event generated from a coronal mass ejection from the sun about 2 weeks ago. And that caused some perturbation to the satellites' orbits, and also some surges in voltage on buried pipelines. So what are the main issues really? We try to not give too many specific examples here, but rather generic examples of coating damage. Obviously, coating damage affects the amount of current that's required. And if the pipeline's been designed on the assumption that it's been properly constructed with normal levels of coating damage, then there might not be enough cathodic protection available to protect all of the coating defects. And of course, some coatings are better than others. And there are sometimes significant problems that can be caused at the coating application plant. For instance, if they're in a bit of a rush and they speed up the process and they quench the pipe before any chemical reactions associated with the coating are complete, then you can get coatings that seriously underperform. There are two kinds of direct current interference. You get what we call the continuous interference, which could come from somebody else's cathodic protection system. And you get those that are varying with time, such as those that relate to movement of trains, for example, or industrial activity like welding at a factory. And then we've got AC interference. And I'm going to talk about each of these in a little bit more detail as we go through them. We'll go through the coatings first. You could see from the little electric circuit that we did of the anode in the soil going up through the test post, through the link, down to the pipe, and then back through the soil. You can see from that if the current is not getting there, then it's possible for current to leave the pipe because there's no cathodic protection connected to it. And as that current leaves, there is a metal loss. And we can calculate that metal loss, and 1 amp DC for 1 year will consume 9.1 kilos of carbon steel. That's Faraday's law, it's not an option. So obviously, we've got to reduce those current paths that leave the pipe through the soil, because that's when we get the metal loss. And we know that if you've got things like stones in, as I mentioned earlier, they will impede that flow because they're a high resistance. So the primary function of the coating, therefore, is to provide a high resistance between the pipe steel and the soil. That's the only thing that we as corrosion people ask it to do. The fact that it has lots of other properties that far exceed the requirements for stopping the small currents from the pipe is, by the way. The only function that we want it to do is to provide a high resistance so that when the coating is intact, there won't be any loss through the coating. But coatings do deteriorate with time, and some coatings are more susceptible to water uptake than others, and they become transparent, electrically speaking. So you have to select your coating with a little bit of care. And I would say the one area in pipeline external corrosion protection that has really advanced in leaps and bounds with the excellent science that goes on now is the quality of coatings. Modern coatings, properly applied, are significantly better than the coatings we had even 10 years ago, and certainly the coatings we had 50 years ago. But of course, we've still got a lot of pipelines around that are over 50 years old with coatings that are of that age too. So they're probably past their best now. Some of them will be totally transparent and will demand large amounts of cathodic protection current. But we can deal with that retrospectively, provided that there are no other obstructions to the current getting onto the pipe. Here we've listed some of the typical areas where coating damage can occur. And these are areas where pipeline designers can have a major influence. Instead of just producing a pipe design that hydraulically is perfect and in terms of control is perfect, the whole thing is useless if we get external corrosion caused by coating damage. And in areas where there is coating damage and it coincides with AC interference or DC interference, our risks spiral. They become huge, because we talk about 1 amp DC for 1 year consuming 9.1 kilos. But imagine, for example, the London Metro, depending a little bit on what trains are running and how many people they're pulling and so on and so forth, you can get currents of up to, say, 600 amps DC. And if you're looking at high-speed trains, then you can get quite higher voltages induced into the pipe, and serious damage can occur. There are examples, too numerous to mention, of pipelines that have not even been able to be put into service because they've had corrosion penetration before the pipe's even been put into service, caused by stray currents. And it highlights the need for temporary protection in order to make sure that everything is going to be tickety-boo before you actually get to apply the full cathodic protection. It means that pipeline designers have to be really aware of the high risks associated with stray currents on pipelines, even during construction, not just afterwards. There are many incidences where this has been a problem. So you have to think, well, how do we get around that? Well, the truth is, if there's no coating defect, you won't get any corrosion. It's not yet possible to have a whole pipeline that's perfectly coated, but you can achieve perfect coatings over short distances in certain areas, because it's very expensive to do, but it's cheaper than having the pipeline penetrated. But it is possible to have a perfect coating over very short distances now with the modern coatings, with the right sort of coating selected. So the poor designer, he has to take into account not only how the pipe is coated in the factory, how it's tested, how it's stored, how it's transported, how it's put on the vehicles to transport it to site, how it's stored at site, how it's protected when it's at site. And if you're working in areas close to overhead power lines with significant power in them, you even need to earth them and protect them from corrosion during the storage and the construction period. So you need to look at it from the moment it goes into the coating process in the factory to the time that it's lowered into the ditch and backfilled. It's really important to try and get that as good as possible. And the modern levels of coating quality and QA/QC and attention to detail in many countries is so good that sometimes we have to add an artificial defect to the pipe in order to get any cathodic protection current to flow. So that really needs to be the case all the time. That would be ideal. The other area where problems arise is on the coating repairs in the field, where people see a small coating defect, or it's picked up with a device you may have come across called a holiday detector. Or it's just basically a spring that wraps around the pipe, and you have a voltage in that spring set to a level that if it comes across any difference in the coating quality, it would give a little jeep, a little noise that goes jeep, jeep, which is why it's called sometimes a jeeping test. In fact, it's a verb in French, to jeeper. They use now in certain countries to indicate that they're doing a jeep test. But then they spoil all that by just going along with a little bit of melt stick or a bit of sticky tape and thinking that's done the job. And it's such a short-term view that the coating defects need to be properly repaired to give you long-time reliability and integrity. The next area where a lot of problems occur subsequently is in the area of field joint coatings. I can't tell you how many people ask us, is it possible to protect underneath the heat shrink sleeve that's come away from the field joint? It's such a common question. And it's possible to make perfectly good heat shrink sleeve field joint coating if that's the way you like to go. Not my personal favorite, but there's absolutely nothing wrong with it if it's done properly. If it's not done properly, then you're stuffed, because once that highly resistive heat shrink sleeve disbonds from the pipe and allows the water to get in and the oxygen to get in, there's a little chemical soup going on there that will encourage the corrosion. And as I'll show you in a little bit more detail later on, the cathodic protection doesn't necessarily go where the water is. Just because water gets in doesn't mean the cathodic protection current will get in. And I'm afraid in the case of disbonded heat shrink sleeves, the solution really is only to keep pigging and keep your fingers crossed, or to expose them one by one and do them properly, which is what you should have done in the first case. And so we need good selection analysis of what's needed for the field joint coating, and good specifications for the application, and good specifications for the testing. Because I say that because of the jeep that's used to do the coating tests is easy to fool. If you just turn the wick down so the voltage is not as high as it should be, you'll always get a good result. And it's not beyond the guile of unscrupulous people to do that. So all of that needs to be carefully specified. And there are other things to take into account with field joint coatings in particular. By definition, they're done in the field and often in difficult conditions for the welders and the applicators. And you have to take into account the mechanical stress as well of the field joint coating that you apply, to make sure that that's compatible with what the parent coating is and what the chamfer is. And you also have to make sure that the product you're using is suitable for the environmental conditions that it's going to be used in. There are some field joint coating systems that can't be used in very wet conditions or very hot conditions or very cold conditions. Some materials need very expensive storage facilities on site, and some need extremely high quality surface preparation. All these things can be done, but there's an environmental and a fiscal cost associated with that. Depending on what your views are on this, you may not be happy with certain kinds of materials used for blasting the surface of the pipe in order to make it clean. And then, of course, there's the obvious installation damage. I mean, how hard is it to build a pipeline? You dig a trench and you drop a pipe in. There we are, that's it. But even the best quality coatings can be penetrated by sharp stones in a trench. So therefore you need to put it in the trench properly. And you need to put some kind of padding in the base of the trench, and all these things need to be specified. An awful lot of the design specifications I see, and not an awful lot, it's not unusual for design specifications not to give specific construction requirements because they leave that up to the contractor. And I think that's wrong. I think that if you have the responsibility for the design, you need to lay out what specifications they need to follow and what they need to do in the way of trench preparations. And with horizontal directional drilling, which is used so often these days, you need to be sure that the coating can take the pressure and the risks it's going to have. By nature, you're pulling it through all kinds of things, and it's likely to get damaged. And there are tests that should be done on the section that's been horizontally drilled before it's tied in, because we can do these external tests, and they're specified in the standard what to do and what's acceptable, and you can tell whether or not it's been damaged beyond protection levels. So that's important to undertake those tests and to specify that those tests have to be undertaken before it's tied in. Casings I've already mentioned. Another area that's come up is the use of weight saddles, because if you need to add some weights onto the pipe in order to make sure it doesn't float and bob around, you need to make sure that the weight saddles don't cause any damage to the pipe, because they will also actually shield cathodic protection current from the pipe. So if you end up with a coating damage beneath a saddle, there's a strong possibility it won't be cathodically protected, and neither will it be detected by above ground pipeline surveys. You just won't know. So that has to be carefully looked at. And similarly, there's a risk if you concrete weight coat the pipe, and if you put any steel reinforcement in, you have to be very sure that there's no chance that the steel reinforcement is going to be in contact with the pipe, because the bare steel reinforcement will apply a high cathodic protection load, which can't be coped with, was not built into the design for the cathodic protection. So these are the standards that you need to be looking at, in my view. For the factory applied coatings, there's 21809-1. That's for 3-layer polyethylene and 3-layer polypropylene. Those are very, very strong, mechanically strong coatings. 21809-2 is for fusion bonded epoxy. 21809-4 for 2-layer polyethylene, and 21809-5 for external concrete coatings. And for the field applied coatings, we have 21809-3, which is for field joint coatings, and 21809-11 are for coating repairs and rehabilitation. Now, I was a member of the groups that wrote the -3 and the -11, and the field joint coating is not really a standard or a specification in the normal sense. Normally, standards are what we call performance related. We say what you have to achieve, and you give you some tips of ways that you can achieve it. But with the field joint coatings, it was just one massive bun fight from beginning to end between coating manufacturers, field joint coating manufacturers. Every one of them with a valid tale to tell, but sometimes more interested in disparaging the competitive, their competitors in the commercial way. So what we ended up doing was making generic groups of field joint coatings, generic types, and then we wrote the minimum testing specifications that were acceptable. And even that was very difficult, because a lot of the products significantly exceeded the basic necessities for the corrosion protection. And the people who made the higher quality coatings were not so happy that they had to comply with the people who were making a much lower specification. And there was really no way around that. It's a difficult standard, but at least if you apply all the factors that are relevant for your own particular application in terms of the parent coating, the chamfer, the environmental conditions, and so on, then you can select a group of coatings that will do the job. And then it's up to you to then select the ones that you think apply and then ask them to do tests to prove that they meet the minimum requirements. The coating repairs and rehabilitation was also a difficult one to write because of the many varied conditions. But we did actually provide you with a matrix to allow you to decide what the residual risks were. And we described some ways of locating those areas that need to be attended to. So for coatings, you really need to follow it. I would suggest the designer needs to really follow it all the way from cradle to grave so that you know that from the very beginning, it's as good as it can be. And then by the time it goes in the trench, it's as good as it can be. And then by the time the field joint coatings are on, that the integrity hasn't been impaired in any way. Not easy stuff, easy to say, but not easy to enforce. So if we look at now the DC interference, we've got the two that I mentioned, the steady state and the time varying. The steady state is often more difficult for designers to understand. And it's all to do with the movement of electric charge in the ground, which is a complex subject in itself. But we're very concerned with voltage gradients. And that might seem a difficult concept, but if you imagine if you have a flat piece of wood and you have a football on one side of it, if you raise one end of the wood, you've made a gradient between the bit you've raised and the bits at the bottom. And on roads, we measure those in percentages these days, but we used to measure them as a ratio, like a 1 in 3, a 1 in 5, a 1 in 10. But basically, the higher you lift that piece of wood, that flat piece of wood, the faster and more easily the ball will roll down. If there's any friction in the ball, you need to lift it higher in order to get it moving, to get a bigger gradient. Well, it's exactly the same with voltages in the ground, except you can't see those. But if you have a big voltage difference between 2 points on the ground, the electric current will go from the higher point down to the lower point. So it's a bit like the football moving down the gradient. And you might say, well, what's all this got to do with anything? Well, if you're building a new pipeline and you've followed all those rules about the coating and so on, you'll have a pipeline that requires very little cathodic protection current to protect it because there'll be very few defects and no connections directly to earth. But if it happens to be close to another pipeline that's 50 years old and needs a lot of current and has big anode ground beds in the ground, the voltage gradients that can be generated from those existing systems can adversely affect your pipe. Now, if the coating's perfect, it will only be a measurement problem. But if you've got a coating defect in that gradient, you are at a higher risk of corrosion. So that's why steady state interference from adjacent CP systems is a concern. And it's something that the designer needs to look at when he's doing his planning. And he needs to get into a liaison with the operator of the pipeline that's taking lots of current in order to develop a mitigation system that suits everybody. That's quite important. Time varying DC from railway systems and all the other things we mentioned before, the tidal variations, photovoltaics, wind farms, space weather, buried DC power cables. That's the same thing, except the gradient's changing a lot. So on railway systems, for example, sometimes it's pointing in one direction, and other times it's pointing in the other direction. And the same location on the pipe can sometimes be losing current and sometimes be picking up current. The voltage can be varying a lot. When you take your pipe measurement, you can see the potentials going up and down. and at a rapid speed, and you don't quite know what to do, because sometimes you stand there and you take the measurement, but there are no trains anywhere around. The reason is that even though you can't see or hear the train, there is still electric current going through the circuit to drive the train. So the train could be several kilometers away, but it's taking current through the railway back to the substation, and that current can be affecting your pipeline. So we have special methods of measuring these interferences from time varying sources, and special calculation and analysis methods to tell us how to deal with them. Railway systems and welding systems, not too bad to deal with really, because in the worst case, you can ask them to stop and start or change the way the rails are configured, and we can do bonds and various things. But you can't do anything about tidal variations. You can't turn the sun on and off for the PV systems, and you can't stop the wind in the wind farms. You certainly can't stop the space weather, and you can't stop the DC from these interconnector cables. But they all create gradients, and we have to deal with them. And it does require special expertise in CP designs to deal with these mitigation systems. And the standard that we wrote, the 21857, we actually put in a lot of calculation examples so that people can use the standard to validate their own calculation models if they want to do them. But it's not easy, and it's easy to be misled. When we make the specifications for cathodic protection, I'm aware of the time, Kate, so I'll move on. When we're looking at the specifications for cathodic protection in the standards, we give the only criterion that's relatively easy to measure, and that's the voltage, the potential between the pipe and the soil. And acceptable levels, they vary, but generally speaking, between minus 1.2 volts as the most negative, and from minus 0.85 volts, which is the most positive. So you can see that's a very narrow band that we're happy and comfortable in. That's 350 thousandths of a volt is the maximum kind of swing that we like to tolerate. So we need to try and do something about that. Now, this is some actual data from a DC traction system in the UK. And the interesting thing to look at is we've got plus 15 volts, whereas actually we don't want to go more positive than minus 0.85 volts. And down here, you've got minus 24 volts, which is a lot more than the minus 1.2 we want. And these periods here, these little static periods, that's when the railway's not operating. That's the nighttime operation, which for most trains, most systems in this country at the moment, is just the period when they're doing the maintenance on the line. So there is a little bit of current flirting around, but you can see that in that period, the pipeline's in the right area to be protected. So the difficulty is, what do you do about all of this? Well, there are things we can do about all of this. And the important thing is you don't have to panic, because there are certain other things we have to take into account, which are the kinetics of corrosion, and there's a kind of inertia. It's not quite like that, but you can think of it as a kind of inertia before the corrosion starts. So you can tolerate these swings of voltage, these spikes, if they're not too close together and if there aren't too many of them, because the inertia or the kinetics of it doesn't allow the corrosion to start. It's just like a fly hitting a windscreen, really. Whereas if you run into a swarm of locusts, you might stop. So we have special methods of dealing with that. This is the one we can't do much about. It's just a graphical example of the coronal mass ejection from the sun, which causes these huge magnetic fields. Here we are in the Earth, which is basically, we have a north and south magnetic pole here. And if it was in a vacuum, this side would be exactly the same as this side. It would be a mirror image. And you may have done those experiments at school as children, where you put a magnet over a piece of perspex and you sprinkle iron filings on it, and you can see the magnetic field. Magnetic fields have a lot of very interesting properties, but one of them that concerns us here is that the magnetic lines of force field never cross. It's impossible for them to cross. If they did cross, it would mean you'd be able to have a north and south pole on a magnet at the same time in the same place. It's just not possible. So what happens is that this part here gets compressed and it gets squashed so that these lines are closer and closer together, which means that the field gradients are much bigger. And we know that if you have a change in magnetic field and the conductor, that you will get a voltage induced in the conductor. So as this magnetic field here gets squashed and then opens up again, then gets squashed and opened up again, and then it might even come in this way a bit, each time that field varies, it induces a voltage in the earth. And that voltage is known as a telluric current. And these telluric currents can affect pipelines and railway lines, because pipelines are long, continuous electrical conductors, perfect, just like a radio antenna, really. And they pick up these voltages and generate voltages on the pipeline, which make it look as though the pipe is not protected. And it's not true to say that it's a huge corrosion risk. It's more of a measurement risk. But again, when you have the regulator breathing down your neck, first thing I'll ask you is to prove it. So what we did in the 21857 standard in one of the annexes, we gave a calculation method to calculate what these voltages would be. Unfortunately, although we spent a lot of time on it and a lot of head scratching, you can't simplify the calculation very much. So unless you've got a background in physics or in matrix algebra, you may struggle to do that. But you can do matrix calculations with calculus, with Excel, if you're careful. And therefore, we put in a calculation model to allow you to calibrate your own calculations. So there are some things that, as a pipeline designer, we'd very much appreciate if you could try to avoid. Not always possible, of course. In the end, you have to live with what you can do. But try and avoid long parallelisms with railways, overhead power lines, buried power lines, anything that's generating a voltage. Even these high voltage DC sources, these so-called interconnectors, you try and avoid being parallel to those systems if you can. Avoid any direct connections with anything on the pipe that's connected directly to earth, because as we mentioned earlier, the very low resistance of the earth will take a lot of your current away that you need for your cathodic protection. And try and avoid getting too close to industrial size photovoltaic systems and power sharing systems like interconnector systems, if you can. You can't always, and we can deal with these things if we have to, but we need to know them in advance. And the things to avoid having in the cathodic protection circuit, if you can, are casings, the weight saddles, the high density expanded polystyrene foam cushions, large stones in the trench, sharp stones in the trench, and any contact with foreign structures. We prefer it if you could avoid all of those things. For casings, because you've got a steel shield around your pipe, it's difficult for us to get any current in there. So you really need to look at your casing requirements very carefully. And if you do need them, then try and have a much enhanced carrier pipe coating quality and strong specification and inspection requirements for the casing end seals. That's what always fails, always. People think they can just go along and wrap a little plastic boot around the end and put a Jubilee clip around it, glorified Jubilee clip, and everything's going to be fine. It won't, it'll always leak. It needs to be properly stuffed with something that's hydrophobic at each end, and then have the boot on the end as well. Spacers cause a problem. I mentioned them earlier. These are the spacers here. They're just non-conductive elements that go around the pipe, and they separate the pipe from the actual wall of the casing. Problem is, if they're not properly installed, as you pull them through the casing, they all bunch up at one end, and then the pipe sags, and then you can get, if you get water in as well, you're doomed. Then there's not much we can do to help. But some things that you can do is make sure that you properly calculate the separation distance for the spacers, because you need to look at the load of the pipe and the weight of the pipe when it's got the product in it, and make sure that the spacers are at the right distance to avoid unacceptable sag and still maintain the separation. A test post at each end of the casing is very helpful for us. If you're connected to the carrier pipe and to the casing, we can take various measurements and assure you that there's still no contact. And increasingly now, people are filling the casings with viscoelastic materials or wax-derived materials or equivalent, but it should be something that's pumped in as a liquid and does not set as a solid, which is the beauty of the waxes and the viscoelastics. They can easily be removed. And of course, if you put vents on at either end, and if you angle the casing slightly, that will help to disperse the water in the future if you wanted to do that. Those are covered in the ISO standard. Weight saddles, that's these bimbos here, they're filled with gravel or some other material to give the weight that you need, and then they're plopped over the top of the pipe. Well, unfortunately, people tend to fill them with anything but rounded stone, and the coating gets damaged. And once it's beneath that saddle, it won't be cathodically protected because we don't have enough current to do it. EPS supports, expanded polystyrene foam supports, are being used more now. I've seen more in the last few years now, in the past 30 years. And the contractors are of the opinion that these cushions will absorb water, and the cathodic protection current will go through the water and to protect the pipe. Well, they couldn't be more wrong. High strength EPS cushions are strongly hydrophobic. And the only path up through the cushion would be through the random small voids that are introduced during the manufacturing process when they throw in bits of carbon. And the capillary action of those will never be enough to get any water to the top of the cushion to provide the cathodic protection. Roughly speaking, cathodic protection, I mentioned earlier, doesn't go easily into narrow gaps. Roughly speaking, it will penetrate in the gap about 3 times the gap diameter. So if you've got a 1 millimeter gap, it will only penetrate 3 millimeters. With these cushions, the optimal size for the capillary action is about 10 microns, about the size of a human hair. And so you can imagine you won't get very far with your cathodic protection. So if you're going to use cushions, put a high quality coating on and protect the pipe that way. That's what the typical support looks like that I'm talking about, so that when the pipe sits in this recess here, there's a little gap at the top between the pipe, and the water gets in, the corrosion goes ahead, and we can't do anything about it. Now here's one which is a double whammy for me. It's got the weight coating on, and it's got the cushions. Goodness knows why they needed to do both. But actually, when I look at it more closely, it's a quadruple whammy, because it's also running parallel to 2 high voltage overhead systems, and there were actually very high voltages induced in the pipe during that particular project. So I'm going to whiz through the AC now. I've got a couple of minutes left. It behaves differently to DC. No big mystery there. It has a magnetic and an electric field associated with it, which were at right angles. And the changing field induces a voltage in the pipeline. Imagine the pipeline running parallel here, and each one of these will induce a voltage into the pipe, which is why if we cross it at 90 degrees, we don't get so much voltage induced. So we know that if you get a a conductor in a varying magnetic field. You'll have voltages induced in it. We discussed that earlier. And although this is a corrosion presentation, I am going to talk a little bit about the electric shock risk, because it definitely is there, and it's something that you as pipeline designers have to take account of. I don't think anybody would be satisfied if you just said in your spec, make sure nobody gets a belt from the electric shock. 100 thousandths of an amp can kill a healthy man, a strong, healthy man. It's slightly less for women due to the way that the blood flows around the body and what the overall electrical resistance of women is compared to men. It's about the only thing left in the universe where we can say we're stronger than women, is that generally we have a higher resistance. I don't know if that's a good thing or not. Anyway, the electric faults that can cause shocks clear very quickly, less 0.06 of a second normally, maximum. You can look at the safety risks in the IEC document here. That tells you more about it. And you can imagine in a situation like this, building so close to an overhead power line, you can easily get high voltages induced, even when the pipes are stored just beside there. And this is an example of how not to earth it, because that spike is supposed to be pushed all the way into the earth, so that as the AC voltage gets induced on there, it finds its way back to earth through the earth rod. So there are lots of ways that we can mitigate against AC safety risks. We can put grounding mats in, and we can make sure that nobody can actually touch anything that's live. And now very quickly to cast and ductile iron pipes. Normally, traditionally, the companies that use these pipes don't apply cathodic protection, because they've got a long track record that says that provided that they're not subject to any external influences, they don't need it, because they wrap it with some covering or other, if you're lucky, and then they just leave it. But in fact, they're very lucky in some respects that they've got away with it for so long. It's mainly because there's a high resistance in the joint couplings, and that prevents the flow of voltages and currents through these short lengths. They're not an attractive path for the stray currents, and also they don't have the high voltages induced in them, because you need a long length to get the high voltages induced. We normally express the induced voltage in volts per kilometer, so that really tells you that these short lengths aren't right. But we do find that cast and ductile iron pipes are sometimes laid near railways in ash and cinders, and you can get corrosion there due to the different elements that occur. It's a galvanic type of corrosion. And the best way is to put on a good butyl rubber polyethylene coating, and also apply the requirements for complex structures, which are much easier to do, because in complex structures, instead of depressing the pipe to a negative value between -1.2 and -0.85, we actually apply a voltage to the soil, and we raise the soil potential, so it has the net effect of lowering the pipe potential. But that's perhaps a story for another day. So gone a little bit over. I'm sorry about that, and I had to rush the last part, but I hope that it's been of some help to you pipeline designers, and be happy to answer any questions. I think, Norman, you've kindly agreed to correlate.
Yeah, I can take it. I just need to confirm with Kate whether we've got time to do it. Can we do a couple of questions, or we will be answering them or via email, Kate?
We can do them now. There was only a couple, so go ahead.
Okay, so we've got 4 questions. The first one is, how long should a modern coating be expected to last before it becomes electrically transparent?
sorry, I forgot I was on mute. I would think that in reality that they would last between 30 and 50 years routinely. Some of the polyethylene and polypropylene ones, I think, would last even longer. Long time.
Okay. Okay. Another question. Would a glass overwrap applied to protect the pipe's coating prior to horizontal directional drilling affect or shield the current? Bore wrap type, glass resin type, sacrificial products, for example?
It's a very good question. Yes, it will shield the current. That's what we really want it to do. We want it to shield the current from both directions. So provided that you're satisfied that the bore wrap will withstand the mechanical rigors of the HDD, then yes, you could use it. There are plenty of other products manufactured by guild members actually that can also be used for this application. It's just a matter of trying to make a perfect coating inside the HDD. We can take care of small defects on the coating, but sadly on HDDs, what you often end up with is a very, very long gash where it's pulled against a sharp rock or something like that for almost its entire length. That's the difficult part, but I would have thought that the bore wrap type glass resin would be quite good if it could withstand the mechanical damage.
Okay, we've got two questions more. What is the effect of conductive contamination within the pipe breaching insulation joints between underground and overground pipelines?
Okay, I think what you're referring to here is if the isolation joint is buried. I think that's probably what the issue is. In these cases, it's actually better to have the isolation above ground, the insulation above ground, and that way you don't have to even worry about the risk of the current jumping off the pipe and zipping around the IJ and then zipping back onto the pipe. You need quite high levels of voltage and current in order to conduct the current around the isolation joint. So it's not really something that you need to worry about very much. And it's something that's very easy to check electrically with an above ground test.
Okay, thank you. The last question is anodic protection. Glass coatings are commonly used for CP in offshore applications. Are you saying that the quality of coatings available today negates the need for anodes?
Again, a very good question. I think you mean cathodic protection plus coatings are commonly used. And I would say no, because we simply cannot guarantee a high quality coating for the entire length of the pipe. We can only do it for short sections. If you wanted to spend a lot more money, even than on cathodic protection, then perhaps you could make it perfect. But I'm not suggesting that the coatings are perfect. I'm saying that you can get a near perfect application for very short lengths. I do know of a company that has adopted the policy offshore of not doing the field joint coatings, because when we do field joint coatings for offshore, the applications are even more difficult offshore than they are onshore, because they're on a barge which won't slow down for anything. So they have to make the welding and the field joint coating very quickly under difficult working conditions. And whatever happens, the field joint coating goes over the stinger in whatever condition it's in. And I know one company that said, well, we're not going to bother with field joint coatings now. We're just going to put an anode near each one and protect that short area because our coatings are so good. And I think that's a judgment that has to really be made by the pipeline operator.
I've got a last question. If modern coatings only last 30 to 50 years, what is the design life of a CP protected carbon steel pipeline expected to be?
Well, thank you very much for the questions. And I do hope it's been of interest to you. And the Guild is obviously the best place to come for a wide range of expertise relating to pipelines, not just corrosion. And the Southeast branch has a very active group that's always presenting new technical notes and presentations. So I would say keep your eye on the Pipeline Industries Guild website for new presentations.
Yeah, I'd like to thank you, Ken, for a very interesting presentation as always, and thank you everyone for joining today. Please look for future events on the website, and then if there are questions that we unanswered, we'll try to answer them online. Thank you very much.
You're very welcome. Bye-bye, everybody.